All right, good evening, pre-calculus. So this is going to be a couple of videos, kind of hoping to supplement people who have to miss because of COVID, so you guys can still get something of a lecture. If you didn't have COVID, feel free to watch the videos anyway. Okay, so today we are going to talk about rational functions. Okay, so let me go ahead and pull this up. I'm going to have to break this up into a couple of parts because unfortunately this is kind of a long topic. Okay, my apologies that it's got to be that way. So here we go. Let's go ahead and share my screen and share it. All right, now this is kind of what I have. Little pad to write things on, and I've got my little pen. Okay, so here we go. So the idea of a rational function, I'm just going to call it r of x, okay, is equal to a p of x divided by a q of x, where p of x and q of x, sorry about that, are both polynomials. Okay, so we're not talking about things with square roots in them as of yet. We're not talking about like embedded fractions inside of a fraction. That can happen, but you know, how hard do you want to make this when we first start? So, but that's what we're talking about. Okay, and the first thing you really want to do, I'm going to call this my 0th step because a lot of books don't mention this, but you need to start off with p of x and q of x have no common factors. Okay, so if I ask you something like, you know, what if we have 15 divided by 35? Well, this is 3 times 5, and this is 7 times 5. We cancel the 5s, that's a common factor. So with algebra and polynomials, more specifically, if I did something like x squared minus 9, and say we had 3x squared, I think we'll do a plus 10x. No, that's not going to quite do it. Those are not going to work. Let's go with easier. How about we do something like x squared minus 5x plus 6. All right, that should do something. So, right, there's an obvious thing to try here. X minus 3, x plus 3 divided by, and then we have to factor the bottom out too, which is good practice anyway. Now we're just forcing ourselves to check. We get an x minus 3 and x minus 2. Does that work? We have minus 3 minus 2 is minus 5. Multiply the top. Okay, we're good. So because we can cancel these, that is now a common factor. Now, everything else we do with this function is going to be on the reduced form of it, okay? Technically, you can go back to the original and work on that, but you're going to have some spots where, like if x equals 3, what's going to happen here? If x equals 3, what's going to happen here? We're going to end up with a 0 over 0. We don't want that. Okay, everybody's not going to be happy with that one. So we need to cancel the x minus 3s, but you can't just like discard it, right? I canceled them, so we're just going to toss it aside and not worry about it ever again. You got to remember that this was part of your original function. Now we're going to treat it like this, except x cannot equal 3. Okay, that's going to be part of this function now because we have a piece of the domain it's just missing. Okay, now the graph is going to kind of get close to this. Okay, so if x were to be x equals 3, just pretend with me for a moment. Okay, what we would end up with is 3 plus 3 for the numerator and 3 minus 2 for the denominator, which would be 6 over 1. So the point 3, 6, this is called a point discontinuity. okay, to point discontinuity, which means there's a hole in the graph somewhere. Okay, so we're doing our graph. This guy here, 3, 6. Okay, this would be a hole in my graph. All right, so the first thing we're going to do is we're going to deal with anything that looks like a common factor so that we can point it out, treat it like a point discontinuity rather than something else. Okay, so that's what we're going to deal with. Okay. Step 2, we go for our rational function to graph this thing, is we are going to determine where, if any, there is a vertical asymptote. Okay, I'm just going to abbreviate it VA now. Again, step 0 with our point discontinuity, that's just the thing we have to deal with. But usually when people teach this, their first step is find your vertical asymptote, because some books deal with this part of it, some books don't. Okay, so I'm telling you because to be more complete about it, I don't think there's too many in your book that does this, but if it comes up, you're going to say, oh, we talked about this. I know what to do with this. Okay. So we're going to take the denominator, whatever the denominator happens to be, and set it equal to 0. Okay. Now, some values, so if I just had the fraction, right, x plus 3, this is a new one. We're just starting with x plus 3, x minus 2. All we're going to do is set x minus 2 equal to 0, x equals 2. That's my vertical asymptote. You can have more than one. What if we had x cubed, or I'm sorry, x squared minus 9 on the bottom, right? Or let's do what else? Let's do an x squared minus 16. Right? If we had this as a fraction, right, we'd have x minus 4, x plus 4 equals 0. Then you could also use square root principle here and just say x squared minus 16 equals 0, x squared equals 16, and x is equal to plus or minus 4. Or you could factor and say, well, x minus 4 equals 0, x plus 4 equals 0, 4 here. So x equals 4, or x equals negative 4. Same thing, right? Same thing. That would be my vertical asymptote. So technically it's the line x equals 4 or x equals negative 4. Remember, if you just have an x equals something, the line is going to be a vertical line. Okay? They don't have to have a vertical asymptote. If I have something like x over, say, x squared plus 1, if I set the, first off, they obviously don't cancel anything here, right? There's no factors to cancel. So if I had x squared plus 1 equals 0, can we solve it? Well, not in the real numbers, because we could have x squared equals negative 1, but now we're in a different realm, okay? And we want to graph things on the x, y coordinate axis, okay? There will be a place in this class where we deal with, x equals plus or minus I, but we have to switch coordinate systems to be able to use this, okay? So when we go to the complex world, we're going to have a real axis and an imaginary axis, right, with the eyes on it, rather than an x and a y. We are graphing on an xy axis. Later on, we may graph on a real imaginary axis. Okay, I know they look similar. There's different things that have similar jobs here, but they're not exactly the same. Okay, so that's why this is Cartesian coordinate system. This is real imaginary axis. Okay, there's other coordinate systems that you'll get to know as well. All right, but for now, this is what we're dealing with. And mostly when we want to graph here, real x and y. So to be proper, there's no real solutions here. Okay, so therefore there is no vertical axis. There's no real solutions. Okay, therefore no vertical asymptote. So those are kind of the easy part of graphing rational functions. Okay, if you see an asymptote, like I know the denominator had a solution equal to 0. Okay. If you don't see an asymptote here, then the denominator did not have a real solution. Okay. So the next part of being able to graph a rational function is the horizontal asymptotes. Okay, and if anybody else other than people in my class are watching this, and you say, wait a minute, can't you just, like, yes, you can, but the class I'm teaching, they don't know what calculus is yet, so we are not invoking anything like limits or anything like that. So if you've had calculus before and you're in my class, like, yes, you can use other methods, but for now, we're going to do it this way. All right. So you could lie to me, of course. You could use the calculus method and then lie to me that you did it this way, because they agree with each other, you'll be fine. Okay, so first condition. What if, so the what if, first condition, we'll say the numerator, the degree of the numerator is less than the degree of the denominator. Okay, so examples, we're looking like 1 over x squared minus 7, okay, x over x squared plus 1, x squared minus 3x minus 4 over x cubed, okay. Again, I'm trying to make sure I'm not getting any common factors here. I mean, that really matters, but again, let's just work on one thing at a time. Okay, so all of these, the degree of the numerator, right, 2, 3, the degree of the numerator is smaller than the degree of the denominator. Okay, we have a horizontal asymptote at the line y equals 0. Okay, so again, y equals a, that's a horizontal line. Okay, so we have a horizontal asymptote at y equals 0. Okay, part 2. Okay, what if, or condition 2, what if the degree of the numerator and the degree of the denominator are the same? So the degree of the numerator okay, so what you're looking for is something like 3 minus 2x over 5x plus 1. The degree of the numerator is 1, the degree of the denominator is 1. Our horizontal asymptote, okay, is 2 minus 2, because that's the leading coefficient of the top, divided by 5, that's the line y equals negative 2/5. That's my horizontal asymptote. Okay, so when you deal with the numerator and denominator, the degrees are the same. It's the ratio, actually, let me put this negative sign here, the ratio of the leading coefficients of the top and the bottom. So a over n, b over n, y equals a over n and b over n are the ratio of the leading coefficients. Okay, so y equals the line ratio of leading coefficients. All right. So now for the fun one. Okay, and again, if you look at that and you say, wait, I know some calculus. This will work just fine, won't it? Okay. So part 3. If the degree of the numerator is bigger by 1, okay, is 1 larger than the degree of the denominator, then we have an oblique or a slant asymptote. Okay, the book I learned out of uses the word oblique. The book that current class uses the word slant. Okay, so it's same thing, just with whichever word you want to use for it, you can do that. Okay, so we have an oblique or a slant asymptote. I tend to use the word oblique, but whatever. Okay, so what we're looking for is something like x cubed plus 1 over x squared minus 4. Okay, so we would have an oblique asymptote. Okay, the way we find it, okay, how to find this asymptote is to take your denominator, x squared minus 4, and you have to do polynomial division. See, I told you this was going to be fun. X cubed plus 0, x squared plus 0x plus 1. You have to do polynomial division. Some people will be able to use synthetic division. The only problem with synthetic division is that the usual algorithm that we learn these days has just has an x minus c at the bottom. So if you're used to using, or if you want to use synthetic division, show off a little bit, that's fine. Okay, but normally I'm going to have something like 5x squared minus 3x plus 1, and we're going to divide it by like x minus 5. Okay, so that would be fine for your synthetic division. But if you've got something that's a little bit more complicated and you don't know how to do synthetic division for a denominator that is not linear, it's quadratic, then you're going to have to use regular polynomial division. Okay, there is a way to go ahead and use synthetic division with something like this, but I'd have to go look it up myself. So I don't use it that often. I just find it easier to use polynomial division, so that's what we do. Okay, examples forthcoming. Okay, I'm just trying to give you an overview of what's going on first. We'll do a lot of examples in another few videos here. Okay, and case 4. Okay, so we have so far, right? We have the degree of the numerator is less than the degree of the denominator. They happen to be the same. The numerator is 1 larger than the denominator. What else do we have left? There's only 4 conditions. Okay, the numerator, the degree of the numerator. Go ahead and put it in like that. The degree of the numerator is 2 or more than the degree of denominator. Now, our book, actually, I think every college algebra book and pre-calculus book we have used in the last 10, 15 years has told us that there is no horizontal asymptote. Okay, ignore that. That's somebody losing a game. Okay. So the degree of the numerator is 2 or more than the degree of the denominator. There is no horizontal asymptote. What we used to do was say that there is something called a limiting function. Okay, now our book, if you're taking my class, you don't have to worry about this. You just say there is none, that's the correct answer. Okay, for a lot of books that colleges are currently using, there is none, that's the correct answer. Okay, however, if your book went off about limiting functions, then you're going to have to do, again, polynomial division. Okay, that's really a joyous thing. But the value you get up here, okay, is your limiting function because it's not a straight line, so we don't say it's an asymptote. Okay, so if it's x to the fourth divided by x cubed, so if we have something like x to the fourth minus 6 divided by x squared plus 1, okay, we would have x squared using the x to the fourth, x squared times. So our limiting function would be some kind of a parabola, okay? But if I ever asked a question like this, I won't because it's too easy, but if I ever asked a question like this, even multiple choice, it would be the correct answer is there is no asymptote. Okay, there is no horizontal asymptote. Now, a couple of things about that. Again, the book that we use tends to make it seem like there could be a horizontal asymptote and an oblique asymptote. That is technically possible, but you have to work your way to make that happen. So what you would have to do is you'd have to come up with a piecewise function where part of the piece had a horizontal asymptote, all right? And then there might be, this could be discontinuous, but there would also be a different piece of this thing that would have, let's pretend that we match them up and everything, that could have an oblique or a slant asymptote. So you make it something like this. Okay, so we're doing that. And then there's some kind of a piecewise thing here. And then maybe we have horizontal down here. Okay, it is possible, but we're going to need an f of x equals two different pieces. Let's say that this value here is 2. So when x is less than 2, we have one rule. When x is greater than or equal to, we have a different rule. But that's the only way that we could really do this. So we don't pile this on top of people who are already learning how to do rational functions. It's a little much, I think. Okay, so it is possible, but in typical pre-calculus textbooks, you are not going to come up with this situation. So when they say, like, is it horizontal and is it oblique? Like, look, if you said yes to one, you're saying no to the other. Okay, so you're not, even though our book makes it seem like, well, there could be both, like, yeah, there could be, but you're really bending, you're really constructing one to make that happen. Okay, and that's just not the kind of problems. I don't think there's any in our book, and I know for certain that there is no teacher assigns anything like this, even if it did exist. Okay, so if they ask about it, like, or if they make it seem like there could be both, technically yes, but there won't be. One of the other questions is, can a function jump its asymptote? Can it go through it? Okay, for horizontal asymptote, yes. We consider horizontal asymptotes to be kind of like guidelines rather than rules. Vertical asymptotes, on the other hand, those are absolute, those are rules. Okay, so because they've excluded something out of the domain. If you have a vertical asymptote and you've got some kind of a function that's doing this, it is possible for something to happen here where it would come back down if this was an asymptote. So it is possible for it to jump, but it will never, ever, 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 ever jump a horizontal or vertical asymptote. Okay. If you are studying electrical engineering, it's a very common function to do something where you would have a signal and it would do something like this as it faded away. We still want to say y is equal to 0, y equals 0, the line y equals 0 is an asymptote. And this crosses it, because I know which function this is, this only crosses it about an infinite number of times, so it can cross a few times, okay? Generally, they don't do this in this book. I think there's like 1 or 2 examples where it does, but I don't know if they're in the homework anymore. Okay, so it is possible, but, and it's more likely to happen than this example up here, okay? With a slant and a horizontal, but it is possible. Can you have 2 horizontal asymptotes? Yes, you can. So you could have a horizontal asymptote that does something like this. And something like this. Okay, and we are going to meet a function like this in when we get, I think, chapter 4, chapter 5, when we get to trig. Okay, so that is possibility, but again, not in this section that you learn them. Okay, this will wait. Okay, so that's like your big 3 things to check for as you are building your graphing your rational function. Is you check. There's a bigger list. Okay, but after that, it doesn't. You can do them in any. You can do all these in any order you want too. But we're going to check for common factors. All right. 2, okay. You do your vertical asymptotes if there are any. And 3, we're going to check for horizontal asymptotes. Or oblique. Actually, horizontal is just a special case of the oblique, because you're going to get y equals mx plus b for your slanted asymptote. And then the horizontal one is just that the m happens to be 0. Okay, so these are really the same thing. It's just one's a special case of the other. Okay, but don't think like, oh, you're just going to put both in. No, I'm not. Okay, so horizontal or oblique asymptotes. After that, there might be some other questions that people would ask, but in general, what you're going to do after that is you're going to plot points to kind of sketch in the rest of the graph. Okay, so, and these may not exist at all. Okay, so those are like your 3 steps to being able to graph a rational function. Okay, check for your common factors, check for your vertical asymptotes, check for your horizontal asymptotes. Okay, that's what you're doing. There's other, like I said, there's other little tricks and things you could deal with, or things that they might ask specifically, but these are your big 3. Okay, so remember those. The horizontal asymptote is the which of the 4 conditions are you dealing with? That's the hardest part about this. Everything else is as long as you remember them, is pretty straightforward. Okay, so I thank you for that. I'm going to do some examples in the next video, so I will see you then. Okay, in the meantime, this will definitely get you quite a ways in your homework. Okay, so thank you, and I will see you in the next video.